Hey everyone, welcome back to my channel. Today I will be discussing the derivative of n tetrated to x with respect to x. If you remember from the last video I just posted recently, we discussed the derivative of x tetrated to n. And this came out to be, if I remember, by dx equals times d of xn minus 1 over dx times ln of x plus x tetrated to n minus 1 divided by x. And we use this using some recursive techniques. It's not a closed form in itself, but another YouTube channel, Sober Math, I think, he uploaded a video with the closed form derivative, which follows that recursive relation. But now we want n tetrated to x, n to the n to the n to the n x times. Let's write that n a bit better. So what would the derivative of a function like this be like? Because now we have the height that's varying rather than the base. And dx, now that's the important part here. We're differentiating, We're finding the derivative or differentiating with respect to x. What would that look like? So last time we used a recursive formula to find the derivative for x tetrated to n. We had it something like fn of x was equal to x to the power fn minus 1 of x. That was the exact recurrence relation we used to denote a recursive derivative formula. Sorry about that. We're going to do a similar approach here for n tetrated to x, which is a bit different, but it can be expressed similarly. I'll use t of x to denote this. And since we know the base is constant, we can keep the base constant again, and we raise it to the power t of x minus 1. You can see it has a very similar form, but we don't need a subscript n because that iteration particularly isn't changing. We want the height at x, we want the height at x minus 1. It's a valid formulation for the recursive relation when you take the function n tetrated to x. So now that we have this form, things get a lot simpler. It's analogous to the last form. We had x to the power fn minus 1 of x, but note that this one looks actually a lot easier because n is a base, it's a constant, so we don't have to differentiate the base itself, unlike the previous case, and we can see that they're not equivalent. Because, well, technically they are equivalent, but their derivatives would not be, because we are differentiating different parameters of the hyperoperation. So now tx to the power t of x minus 1, and I want to rewrite this equation in terms of Euler's constant. So we'll use e to the power t of x minus 1 times ln of n. That ln of n, instead of ln of x like last video, will play a huge factor, as you will notice. But now we want to remember that if we have a function f of x is equal to e to the power something interesting. We can actually determine a closed form based on the properties of, well, first we have the recursive form, which we can write down as ln of n times d of n of x minus 1 times n of x. This is a closed form derivative analogous to the result we acquired in the previous video. To work on my spacing, I use this tool. Times n of x. Okay, but note that this term, similar to right above d of n of x, we know that d of n of x minus 1 also will have an ln of n term. It's a very important observation to make to derive the closed form. It will also have another factor of ln of n. Each level down you go, and it also has you multiply d of n of x minus 2 now, times n of x, n tetrated to x minus 1. So we can unroll this recurrence, right, d of x minus 2 and divided by dx. X tetrated to n minus 1. Or n tetrated to x minus 1, I should say. X minus 1. We can see that n tetrated to x keeps getting multiplied with the reducing tetrand. The x, or the power, keeps reducing by 1 in each previous derivative. So and we know the derivative of n tetrated to 0, which is n of x minus x. That's just n tetrated to 0 is 1. That should give us derivative equals 0. We know it doesn't multiply till the derivative of 0, so it starts from 1, the index. Yeah. Which should... Now let us focus on the first part of the recursive derivative, which is we had ln of n. For the first time you unroll the recurrence, and then when we see for n minus 1, we find another ln of n for d of n tetrated to x dx. Let's see. We have ln of n at first, and then we know it's multiplied to d of n of x minus 1, so there's another ln of n, and it keeps getting multiplied to n x minus 2, x minus 3, x minus, until we reached x amounts of ln of n's, and then there is nothing unless we collapse the whole product. There is no more. It goes from 1 to x number of ln's that we multiply itself to. X times 1 time. So we can see that for the derivative of n tetrated to x, we have x products of ln of n's, or ln of n is multiplied to itself x times. So we can formally, and then we know that the tetration itself, n of x, is multiplied by n of x minus 1, n of x minus 2, all the way down till 0, because n of x minus 1, x minus x is 0, which is n tetrated to 0 is 1. So we have ln of x, and then we know it's multiplying a bunch of tetrations of n of x, and to the n tetrated to x minus x, all the way till 1. So that would mean n tetrated to x, n tetrated to x minus 1, and then you end the product with multiplying with n tetrated to 1, which is n, and n tetrated to 0, which is 1. Obviously, what I meant by collapsing the product, I think I was referring to n tetrated to minus 1, which is a base case, and it leads to 0 in tetration, unlike exponentiation, which has different values depending on the base. So summing all this up, we can say that d of n tetrated to x with respect to x is equal to ln of n. Right here, actually, it should not be ln of x. Raised to the power x times, multiplied by a product we can set the index as 0, because n tetrated to 0 is just 1. All the way till x of n tetrated to I. Ooh, I think I should set I there. Small correction. This is a pre-recording, so that it should be, in the product, it should be n tetrated to I, not x, because the I is what's changing. But, yeah, thank you.